Okay, hi guys, so in this lecture we'll be discussing on photochemical reactions. So let's get started. Photochemical reactions. So suppose we have HBr, which in presence of H nu gets dissociated into free radicals H dot and Br dot, and similarly Br2 in presence of H nu gets dissociated into Br dot plus Br dot. So the rate of reaction in this case is proportional to the intensity of the absorbed light. Okay, rate of reaction in this case is proportional to intensity of absorbed light. Okay, so which is denoted by AIABS, intensity of absorbed light. So rate is equals to I absorbed light times phi, where phi is the quantum yield. There is no unit for this quantity. So IABS is number of moles of photons absorbed per unit volume per unit time. Absorbed per unit volume per unit time, and phi is nothing but quantum yield, which has no unit. And phi can also be written as number of reactants consumed divided by number of moles of photon absorbed. Number of, not reactants, rather number of moles of reactants consumed divided by number of moles of photon absorbed. Okay, and now we will be seeing the factors that those can influence the rate of reaction. Those can affect or influence rate of reaction. Okay, so first is concentration. Except zero order reaction, because in zero order reaction we don't take the concentration of reactant as the power of reactant, or rather the power of concentration of reactant is 0. Second, pressure of gas. Third is temperature. Fourth is catalyst. Fifth is surface area of solid catalyst or reactant. Okay, and we can write that more the surface area of solid reactant or catalyst, more will be the number of active site for reaction, and higher will be the rate of reaction. So we can write more surface area would have more number of active site, and higher will be the rate of reaction. Okay, and sixth point is the intensity of the absorbed light in case of photochemical reactions. We have just seen intensity of absorbed light in photochemical reactions. Okay, now let us see a method which is, we have already seen this method, which is RDS method. So RDS method is the slowest step which is required for the completion of the reaction. It is the slowest step in the course of reaction. Second, the steady state approximation method. Which is during progress of reaction di by dt would be equals to 0, or the I is the intermediate product. So we take during progress of reaction di by dt would be equals to 0, where I is the intermediate constant, intermediate product rather, which we have taken as a constant quantity, and no intermediate product should be present in the final rate law expression of a complex reaction. So some notes here that no intermediate product should be present in final stage, in final rate law rather, rate law expression of a complex reaction. Okay, so let us take an example in which we have a gaseous complex reaction. For an example, we are taking 2 moles of NO2 reacting with F2, forming 2 moles of NO2F. This is a gaseous complex reaction. Okay, so proposed mechanism is as follows. In step 1, NO2 reacts with F2 to form NO2F plus F. So this is the RDS step, as this is a slope step. And in step 2, this NO2 again reacts with F, which was the intermediate in the previous step, Rate constant for this reaction is K2 to form NO2F. This is a fast process. Okay, so we'll be discussing more on this proposed mechanism in the next lecture, where we'll be covering the two methods which we have discussed in this lecture on finding the factors that can influence the rate of reaction, which was RDS method and steady state approximation method. So with this, we come to the end of this lecture. Till then, good luck and goodbye.